Alright guys, so hope you're doing well in this tough times. But anyway, so in today's video I'll be discussing something very interesting. So some of you may have been wondering, I have been wondering for one. See, string theory and loop quantum gravity. These are the two best theories we have best candidates we have for a final theory, for a theory of everything in physics. I slightly discussed the idea of a final theory in some of my previous videos. If you are not aware, it's simply just a theory which will unify all the forces of nature in a single, all the forces, all the interactions, all the particles, everything in nature, it will unify in a single theoretical framework. That is called a final theory. So everything you can explain on the basis of this final theory. Right? Each and every interaction that is possible in our universe. And not just that, a final theory must answer the questions which are not yet answered in physics. It must solve the problem of quantum measurement, and it must there are some other problems in physics like dark matter, dark energy, where are these things coming from. So it must resolve all of these problems. Only then can we call it a final theory. Right. So the question is, what is string theory and what is loop quantum gravity? First of all, just a very basic introduction, because obviously I myself don't know the technical details, so I cannot give them to you, and even if I knew, I wouldn't have given them to you. So I'll be assuming that you are aware of the basic history of physics, like quantum mechanics, the development of the quantum revolution, how the particle nature of light and all these things. I hope you are aware. So, but what is the starting point of string theory? So basically, see, string theory, the basic idea is that, so we have been seeing the standard model of particle physics. That's a very successful theory, standard model. So basically, what the standard model establishes is that there are some particles which we call fermions. These particles make up the matter which we see around us. And there are some particles which is called bosons. Particles, and in the sense particles are unified in quantum fields. This is emergent from the quantum field theory. There are fields, and in the fields there are vibrations, and this gives rise to particles. So these particles called bosons, they give rise to forces. They are, the exchange of these particles gives rise to forces. So forces is seen as due to the exchange of some particles. Suppose between two fermions one boson is exchanged, so that will give rise to a force, can be repulsion or whatever. So like this, the not grand unified theories exactly, that's wrong to say that. I'm talking about the standard model. Grand unified theories is another class of theories, but somewhat similar. So the standard model explains all the three forces of nature: electromagnetic, weak nuclear and strong nuclear, except gravity. So what is gravity? Now we don't know. We know what is gravity. The best explanation we have is Einstein's general theory of relativity. That's a pillar of physics. There are two pillars of physics currently. One is Einstein's general relativity and the other is quantum mechanics. Now string theory, loop quantum gravity, these are all, we cannot say these are verified theories. These are pillars of physics, we cannot say, because these theories are just ideas, just hypotheses. They are beautiful, they are elegant, the mathematics works, and there are reasons to believe in them, but still they are in development, and they have, as of now, they have not given any testable predictions. So we cannot say that they are we cannot give them the status of general relativity or quantum mechanics, because both of these theories have been experimentally tested, and they are old theories. They are verified, and mathematically, theoretically, practically, they're verified. So that's it. And there are very little problems. In general relativity, there is almost no problem with the theory. Quantum mechanics, there are some problems, but it's actually a very successful theory. So anyway, so general relativity explains gravity. I might have bored you by saying so, but let me say it once more. Gravity is now there are recent theories, modern theories, that gravity can be due to the surface tension energy and all these things, but I will not go into that. According to general relativity, gravity is simply arising due to the curvature of space-time. Here the crucial point is to understand the background dependence and background independence. So in classical physics, what we did in Newton's time and everything, we assumed that there was a fixed background, and on this background everything is happening. Motion is taking place, velocity, particles, everything is happening on a fixed stage, on a fixed background, but the stage is not changing. The stage on which the drama is taking place, the stage is not changing. So such kind of theories are called background dependent theories. And although I said that this is the case for older theories like classical physics, even string theory is background dependent. So in string theory, what we assume that there are some, I'm coming to that point before the general relativity. So, but in general relativity is a background independent theory. Why? Because in general theory of relativity, there are no fixed conditions, like there are no fixed equations, there are no fixed values of the background which you must set. The background can evolve, the background can change, the background can curve. The background means what? The space-time. So the space-time can curve, the space-time can evolve, and the space-time is directly interacting with the matter energy. The matter energy is affecting the space-time, and the curvature of space-time is affecting the presence of matter energy. And these effects are giving rise to the gravitational interaction. So it's a geometrical sort of force, emergent out of the curvature of space-time. So again, emergent force, there are many, like emergent I am saying in a very rough sense, like don't take the word emergent too seriously, that's again another topic. So, but yeah, gravity may be emergent, obviously, gravity, all these things, space-time may itself be emergent, we'll be coming to that, loop quantum gravity, that emergence is a very important concept. So that's the basic thing, guys. Now what is the point? So general relativity is background independent. Now so we have two categories of theories, background dependent and background independent. Now see, what should we do? Like, should we go with background dependent theories or background independent theories? The obvious answer is background independent theories. Because in background independent theories, the structure of the background is automatically arising out of the equations, out of first principles. You don't need to explain that. And if you are trying to find a final theory, a fundamental theory of nature, then obviously you shouldn't have any values which you are putting it. You shouldn't like a standard model. Standard model cannot be a final theory because it has a lot of values which we need to adjust, which we need to put it, which we need to find out experimentally. But a final theory, fundamental theory means what? Everything will be coming out from the framework of the theory itself. We need not plug in the values. We need not, the lesser the number of values we have to plug in, the better for a fundamental theory. I hope you are understanding. So that's the problem. Like that's what I'm trying to say. So yeah, and that's all about like background dependence and background independence. So in a background independent theory, I hope this is your understanding. In a background independent theory, there is no fixed condition on the background. The background is itself evolving. The background is itself part of the theory. But in background dependent theories, the background is fixed. Only on fixed background, particular backgrounds, the theory can be explained. So obviously this does not seem fundamental, background dependent theories. So that's it. Now, so this quantum mechanics then it was slowly incorporated in the quantum electrodynamics, quantum chromodynamics and standard model grand unified theories, and then theories of quantum gravity were started. So in this video, the main question is that whether string theory is a better approach or loop quantum gravity is a better approach. Now in this theory, in this video, let me tell you that I will be presenting some personal views, and I may be biased in my talking, because obviously I have perceived the world from my perspective, so I may be biased, I may be extremely biased. So don't take everything with a pinch of salt. Don't take anything too seriously. Just my opinion, personal opinion, nothing else. So now let's come to string theory. So according to standard model, so far particle physics, we have learned that everything they are arising out of fields and particles and these things. But string theory says that this is not the correct opinion, correct explanation. String theory says that there are fundamental strings. Strings means what? One-dimensional strings. Strings cannot be zero-dimensional. A point is zero-dimensional, but a string is one-dimensional, right? So everything is fundamentally made up of one-dimensional strings. This is the first thing. Now, second thing is that strings can be closed, they can form a closed loop, or they can be open, like an open string, normal open string. So this open string, suppose consider an open string, like just a line in the sense a string, this sort of string. One end can be a particle, like what we are perceiving as a particle. The other end can be what we are perceiving as a particle, and the middle can be these particles are connected by some forces. So like this you can imagine. These closed strings, they give rise to gravitons. Now gravitons means the particle that is responsible for the gravitational interaction. We haven't found such a particle experimentally yet, but yeah, that's the theory. So that's the graviton. Now in this way, string theory, you see, unifies the gravitational interaction along with the other three interactions. So there is some hope that it is a final theory of nature. Right, because and then there were many versions of string theory which were discovered, like superstring theory, supersymmetry. First of all, string theory, supersymmetry had to be introduced. Because why? Because string theory, there were tachyons. Tachyons are particles which travel only faster than light. So these particles have rendered the theory unstable, very unstable. So they had to be eliminated. Now this is a mathematical process how they were eliminated. We will not go into that here. Then there were some other problems with the theories. Like these theories, they require, like, first the bosonic string theory and everything, not heterotic, bosonic string theory, if I remember right. It requires 26 dimensions, 25 space dimensions and 1 time dimension. But we know that there are 3 space dimensions and time is a 4th dimension. So where are the other dimensions? One explanation is that they are curled up. They are curled up to very small size. But then the mathematics of the theory requires that these dimensions, these small curled up dimensions, they can grow bigger such that they become visible, or they can shrink into singularity. So both of the situations are problematic. So we have to stabilize them. Some later versions of string theory like this, when you incorporate supersymmetry means every boson has a fermionic partner and this sort of idea. There's a symmetry in nature. So it's a very, very profound idea, very important idea. So supersymmetry string theory says that you need only 10 dimensions, not 26, 10. That's better, but still 10 dimensions you have to explain. So, and then in later M theory, you needed 11 dimensions. To further unify the different kinds of string theory into a single string theory, we needed a further dimension. We have to add 1 dimension. So 11 dimensions. So yeah guys, and so that's the point. Like string theory is not a unique theory. There is not only one theory of string. That if it is a unique theory, then there is a very high probability that it's a final theory. But there are many versions of string theory. So it is possible that all these versions are emergent from some deeper theory, from some more fundamental theory, which is our theory of everything, which we are trying to find out. Now the thing is that this string theory is background dependent. Background dependent means the background is fixed. Everything is taking place on the background, but the background is not changing. It is not affecting the background in any way. Obviously, this assumption is wrong because the background is itself space-time. So the movement of string, gravitational force is affecting the space-time, obviously. So what we do to account for the disturbances, the small disturbances, we use perturbation technique. Perturbation theory means suppose if there is a small disturbance, then you can use the original concept with some extra added terms, and you can use the mathematics. It's a mathematical theory. So in string theory, we use perturbation techniques, perturbative string theory, that's there. But still, it's the background dependent theory, no point denying it. So again, there is some hope that all these different versions of string theory, they are emergent from some deeper theory which is background independent. Because this deeper theory has to work in all the possible backgrounds, so it has to be independent of the background. So today we are seeing string theory is background dependent, but the final theory, the even more deeper theory, underlying theory, it's background independent. That's something, if it's so, then it's very good because we need a final theory to be background independent, right? It cannot be background dependent. The other approach is that loop quantum gravity. Now loop quantum gravity loop quantum gravity again, it makes some testable predictions. Like string theory has made no unique prediction. Like string theory has made some predictions, but if the predictions are true, then we cannot conclusively say that string theory is true. And even if the predictions are false, we cannot conclusively say that the string theory is false. So these are not meaningless, these are not meaningful predictions. These predictions are of no value basically, right? So, but loop quantum gravity again loop quantum gravity has some problems because it has not, as far as I know, there are no any viable predictions of loop quantum gravity, but still it makes some testable predictions. So there is a way to test it. And loop quantum gravity, the basic idea is that you are saying that in string theory, we are assuming a fixed background, space-time is fixed. In loop quantum gravity, we are saying that space is not fundamental, space is not a fixed background. Rather, space is emerging. This emergent again is a very important concept. Space is emergent from some deeper structure. It's not like some of you might think that string theorists do not believe in loop quantum gravity, and loop quantum gravity, there's a sort of conflict. It's not actually this case. Both these theories can be applied together. Some physicists are already doing it, right? Because they're trying to apply the methods of loop quantum gravity on string theory, and that's a very good approach. So I took an interview of the renowned string theorist Edward Witten. He is a great string theorist. So even he said that space-time is in some sense emergent from some deeper structure. So most string theorists also accept this fact that space-time must be emergent to explain all the phenomena. Now, how this can be emergent in terms of physics, we can understand maybe something akin to the ADS CFT correspondence, anti-DC to space conformal field theory. So that's a correspondence. We have a holographic principle, holographic duality. I have made some videos about it, so you can check them out. So just a second. Yeah. So yeah, and so like this is the thing, but obviously only ADS-CFT correspondence is not enough to explain emergence. Like we don't understand exactly how the space-time is emergent, and it's my personal opinion that if we ever understand that how space-time is emergent from some deeper structure according to loop quantum gravity, then this emergence can also indirectly shed light on the emergence of consciousness, because consciousness is also, according to me, an emergent phenomenon. So that's something. So this is why I personally think that loop quantum gravity is a very promising approach. I am not saying that string theory is not a promising approach, but string theory, there have been a lot of research, but no successful predictions till now. And yeah, maybe there are like these ideas like higher dimensions and everything is string like. These ideas are definitely insightful. These ideas, but as a theory, I don't think string theory, because it's background dependent for one thing. So if you say, personally, I am very much in love with loop quantum gravity. I'm researching it in more deep level now. So initially I thought that string theory was very interesting. It's all this, everybody's crazy about string theory. Like what is string theory? Maybe it's the ultimate theory. But now I think that we should also spare equal attention, if not more attention, to loop quantum gravity. And not just string theory and loop quantum gravity. Like even loop quantum gravity has many problems. But yeah, that's for another day, for another video. So that's all, guys, I wanted to say in this video. So I hope I hope the discussion was, insightful and everything. So I don't know, but yeah, I obviously if you are a layman, then it's not possible to, these are very technical topics. So string theory, loop quantum gravity, but I tried to explain the basic story of physics, the current situation in physics in simple terms. So loop quantum gravity basically says that, like in quantum theory, we have seen that everything is divided into discrete packets of energy called quanta. Similarly, loop quantum gravity says that this space is emergent from some deeper structure in the sense deeper building blocks, discrete building blocks. From there, space is emerging. Like space is not a continuous as we seem to be. That's again a good approach. That means you are trying to apply the principles of quantum mechanics to gravity. That's why it's called loop. Loop means that's why it's called quantum gravity. And loop in the sense, like there's a loop, a sort of network of coordinate system. Space is represented as a loop, sort of. So that's why it's called loop quantum gravity. So, and in string theory, we already saw that this force, particles, everything is emerging due to interaction between strings. Suppose two strings are colliding or everything, like very interesting ideas, cosmic string. So definitely good idea to explore these ideas. But that's all for this video, guys. Thank you.